how you call this. Okay, let's continue. So previously we just went through the selection of power transistors, and then the next very important component in the switching power poles should be power diodes. So I also mentioned, right? So for power diodes, sometimes we call it uncontrollable, which is because we don't need to inject any signal to turn it on. Once the voltage variety is correct, the current can flow through. Okay, so here is the symbol. Oh, sorry. So here is the symbol of the diode. So A stands for anode and K stands for cathode. I hope that you know what is anode and cathode, right? Okay, so we have different definitions in terms of here is the electronic circuit. Okay, we have the anode and cathode, and in chemistry we also have the other definition of the anode and cathode. Okay, yeah. So no matter how this is the symbol of the anode. Sorry, this is the symbol of the diode. Okay, so here actually you may find that it's quite like a arrow. Okay, so the tail of the arrow is the anode. Okay, and then the head is the cathode, and then the current flow from anode to cathode. And then this one is a typical IV characteristics of diode. Okay, and so here from this symbol we can see that it is a two-terminal device, while the transistor is a three-terminal device. Okay, and then during its operation, similar to the transistors or the MOSFET, so it acts like a low resistor. Okay, and then the current flow direction can only be one. Okay, unidirectional flow. Okay, and then when the current flow pass through the diode, there will be a voltage drop. Okay, voltage drop. So here for your reference, so previously when I studied in the secondary school, I still remember the value of the 0.7 volt. Okay, but actually this is not a must. It depends on the materials used for the fabrication of the diode. Okay, so if the material is silicon, the voltage here, the voltage here is 0.7 volt. Okay, 0.7 volt. Sorry, this is not a voltage drop. Okay, this is we may say that it is a threshold voltage. Okay, so beyond that, the diode is on. Okay, beyond that, the diode is on. So 0.7 volt for silicon and 0.3 volt for germanium. Okay, so it depends on the materials we use. Okay, and then it can block the reverse polarity voltage, of course, right? Yeah, it is because diode only allows the unidirectional current flow from anode to cathode. Okay. Okay, so actually for diodes there are also many types. Okay, and here we just give you four types. So the first one is the light frequency diodes. So from the word light frequency, so it is not that difficult for us to imagine it should be used for low switching application, right? Light frequency, right? Light frequency should be only 50 to 60 hertz. Okay, and then it has a relatively high on-state voltage drop, 1 to 3 volt. Okay, just reference, it depends on the configuration, materials of the device. Okay, and then the second one is the fast recovery diodes. So again, from the word, it's quite easy for us to imagine its application, right? So it should be good for fast switching. This is because its switching loss can be relatively high, even though the switching frequency is high. The switching the switching loss here low. Yeah, it is because I think in one of the slides in our last lecture last week. Okay, so when the switching frequency is high, its switching loss should also be high. Okay, but that's not the case for this kind of device. So even though when the switching frequency is high, its switching loss is still low. Okay, so this one is very good for switch mode converter applications. Okay. And then the third one is the Schottky diodes. I don't know if you still remember. I believe that you should have learned it before. Okay, Schottky barrier. It is very famous. Okay, it's very famous in physics or even electronic circuit analysis. Okay, so here we have the Schottky diodes. So Schottky diodes have many advantages, okay, when compared to other diodes. So for example, is on-state voltage drop is very low. So when compared to these two range, there is a difference of an order of magnitude, right? Here is just point something volt, but here start from 1. Okay, although those values only are for reference, but we can see that or we have some ideas. Okay, and then it is very good for extremely fast switching. Okay, and the switching loss is also very low. Okay, so for this one, it is very good for very low output voltage applications. Okay, it is because for this kind of applications, if sorry, there's a phone. Let me just turn off. Okay, yeah. So for this kind of applications, so it is because the output voltage is very low. Okay, if we use other diodes with a relatively high on-state voltage drop, then the output voltage should be negligible. Okay, right? So it should be very low. So for this kind of applications, we tend to use Schottky diodes because of those very excellent characteristics. Okay? And then similar, it has also we can say that it is a sister. Okay, it is because the names are identical, but using different materials. So for this one, we still use silicon, and then the relatively new generation is the silicon carbide. Okay, silicon carbide. Okay, so for using the silicon carbide based devices, actually here we can see is pros and cons. Okay, yeah, it is because all the things I think there should have no absolute advantages. Okay, it depends. It depends on what you want to compare. Okay, so here just for your information, so I try to show you the comparison, not all the comparisons, but here just some representative comparisons between silicon carbide and silicon. Okay, and actually, I think many years ago, maybe up to 10 years, okay, the scientists um, they did the research for a long time, okay, um, but they also want to do mass production, right, for industrial use. So curiously, in US there is a silicon carbide value, okay, but I don't know if it grows like silicon value, okay. Okay, so anyhow, for using silicon carbide based devices, it will have these advantages. So we can see that it can operate with very further high frequency, and its electric field is higher. So for this one, do you still remember the first breakdown? Right. So if the critical electric field can be higher, So it means that it's not that easy for this kind of device to suffer the first breakdown. Okay, and then higher thermal conductivity, it can affect the production line or the operation characteristics of the device. Okay, and then higher temperatures. So yeah, that can be related to the second breakdown, the thermal effect. Okay, and then energy density. So it means that for using the silicon carbide-based devices, if uh, both when compared with the power level, if the power level is the same, okay, so the size of the silicon carbide-based devices can be smaller, okay, and then high efficiency, lower losses. Okay, so those are the advantages of the silicon carbide-based devices when compared to the silicon one. Okay, however, the yield is not that high when compared to the silicon-based devices, so the cost is high. The cost is high. Okay, and then although both device configuration principle are very similar. Okay, the production line of the silicon carbide-based devices should be different. Okay, which is because it needs a high temperature packaging technique. Okay, so the packaging method is quite different from the silicon-based devices. So that's the trouble. Okay, it is because for industry, if they want to develop something new, okay, they tend to use the basic or the existing production line, right? But to develop silicon carbide-based devices, they need to uh, build the other new production lines. Okay, so this is also a very major barrier for industry to further develop. Okay, so for your reference. Okay, so once again, we see this picture. Okay, so now we just went through the selection of the power transistor, right? And then we also just learned there are in general four types of diodes. Okay, so now for this application, say for example DC-DC converter. So for this one, we should not use light frequency diode, right? It's because we need the switching frequency is really high, okay, for switching. Okay, so now we should know how to select the appropriate transistor and diode, okay, for DC-DC converter use, or later other applications. Yeah, and okay, so back to here. So before we learned how to turn it on and off to influence the operation of the converter, we should here we should see that. So when Q is equal to 1, still remember. So we use the Q signal to control the transistor on and off, just like uh, at the very beginning we use the Q signal to turn on or off the switch, right? So here, transistor and diode, the only controllable device is the transistor here. Okay, so for example, let's take MOSFET as the example here. So we need to apply the gate voltage to turn it on, right? So when Q is equal to 1, this is on, okay, and then the current can flow from drain and into source to and then to the inductor, okay? And when Q is equal to 0, it is off, right? So there will be no current going through here, okay? So now we try to look at the turn on and turn off characteristics of the switching power pole, okay? So again, we call this switching power pole, right? Switching power pole. Okay, so here it is because MOSFET This one in this topic, we usually take MOSFET as the example of the power transistor. Okay, and then here this statement states that so the switching characteristics of MOSFET actually are dictated by a combination of factors. So it's mainly the speed of charging and discharging. Okay, so it means that to turn it on, we need to do charging. Okay, to turn it off, we need to do discharging. Okay, and then here, just like a Q signal here. So this is the source. Okay, this is the source for gate voltage. So it can be from 0 and then to VGG. Okay, and then for the resistance, we call it out gate. So it is equal to the summation of the RGG and an internal gate resistance. Okay, so before turning on, so all the things should be off, right? So now we want to turn on. We want to see uh, the phenomenon when we turn on the MOSFET or the converter. Okay, so here is the MOSFET, and this one is the dial, and this one here is the constant current source, and this here is the DC input. Okay, so before turning on, so it means that the state of the MOSFET should be off initially, right? Initially it is off. So what happens when it is off? So when it is off, no current flow from drain to source, right? And then when it is off, it's open, right? Just like a open switch. Okay, that you still remember the content in the previous slides. Okay, so it is open, so it means that it can block the input source. Yeah, here is the DC voltage. Okay, and here is the constant current source. So it means that the current continues flowing out. Okay, and here is the dial. So the direction it fits. Okay, so it means that here is a closed loop. So we have the word here. Okay, so the current here I naught fuels through the dial. Okay, fuels through the dial. Okay, so again, before turning on, here is off. So when it is off, there is no current, and here is open. Okay, so instead, here we have the closed loop. Okay, so closed loop with a constant current source. So it means that the current here, we have the term fuels through the dial. Okay, fuels through the dial. Okay, now so at the very beginning we have this. We are here. Okay, at the very beginning we are here. Okay, so let's check. So here VDS at the very beginning is equal to V in, right? So this curve is VDS. Okay, and this one I will use the other color. Change. Okay, so this one is string current. Okay. Okay, so at very beginning, VDS is equal to V in. Okay, correct. Here is V in, right? So I always think this picture is not very good. So here is the V in. Okay, so V in. Okay, at very beginning. And then how about the drain current? So drain current, there's no current flow through drain and source. Okay, so ID at the very beginning is equal to 0. Okay, and here now is off, right? So we have no gate source voltage. Okay, so that's the first one. Okay, and then now we want to turn it on. Okay, so want to turn it on. So we need to go through the first region. So we call it turn on delay time, TD on. Um, Actually, I mentioned before, so to turn it on, we need to do charging, right? It is because there should be a capacitor. Um, Actually, MOSFET for semiconductor materials, we can consider it as the capacitor. So here, very similar, we need to do charging for the capacitor. Okay, so and for the MOSFET, we uh, consider its operation into three regions, right? So the first regions should be below the threshold voltage, right? Below threshold voltage, nothing happened. Do you still remember? Okay, so when the gate source voltage is below the threshold voltage of the MOSFET, nothing happened. Okay, so when we increase the VGS from 0 to VGS threshold value, okay, the threshold value of the VGS, nothing happened. So ID is still 0, and then VDS is still equal to V in, okay? And so this is the first region, okay? And then the second region starts from the threshold value of the uh, 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 gate source voltage of the MOSFET. So second region, beyond this value, ID is proportional, right, to the voltage. Do you still remember? Okay, so here same. Okay, so beyond the threshold value of the gate source voltage of the MOSFET, we have the drain current. So it means that during that time or the period of time, so the drain current start flowing through drain and source. Okay, drain and source. So here ID is linearly proportional to the VTS. Okay, and but at the same time it's still off, right? It is because it is not on yet. Okay, so during this region we call it current rise time. It is because the drain current start to increase. Okay, start to increase. Okay, so it means that here the drain currents is starting to flow from the drain and then to source and then to here, okay, to the current source. Okay, however, here we have the statement: as long as the diode is conducting a positive net current. Yeah, it is because here we still have the constant current source to flow the current out and then go through the diode. Okay, although we have the drain current flow here, okay, but the current, but the magnitude of the drain current is still small, okay, when compared to this. Okay, so once there is a net current, so the voltage across it is still 0. So it means that VTS is still equal to V in, okay, during this period of time. Okay, and then what is the third region of the MOSFET? The third operation region of the MOSFET. So so that is the linear region, right? So the the description of that region is like this. So if we want to want the MOSFET to carry a specific level of drain current, we need to apply the corresponding level of the gate voltage, right? Okay, so now here the target should be I naught, right? So it means that if we want the MOSFET carry I naught, we need to apply VGS with the blanket of I naught. Okay, so it means that at this point, ID should be equal to I naught. Makes sense, right? Okay, so when VGS is equal to this value, ID should be equal to I naught. It is because of the definition of the third operation region of the MOSFET. Okay. So here, up to here, we call it voltage for time. Okay, voltage for time. Okay, it is because when ID is equal to 0, so when ID is equal to 0, so it means that this diode has no more latch current, right? When ID is equal to I0, right? So no latch current will flow through the diode. Okay, and at that time, the diode become reverse bias. Okay, reverse bias. It is because there's no more currents flowing through. Okay. So at the same time, VDS will drop, okay, to 0 eventually. Okay. So that's how we can see the turn-on characteristics of the switching power pole. Okay. So it can be divided into 3 regions. Okay. So the first critical points will be the threshold value of the VGS, and then the other first critical points should be the corresponding level of the VGS to let the transistor carry a specific level of the current, drain current. Okay, so up to here. Oh, okay. After this statement, okay. So up to here, we consider the power pole is completely on. Okay, it's completely on. Kim Hong asked one more time why ID drops to 0. Why ID drops to 0? Let me see. No. No. Here is oh, I may use different color. Okay. Green for this one. This is VDS. Okay. And then ID. Okay. So at the very beginning, ID is equal to 0. It is because initially the MOSFET is off. Okay, so ID would not drop to 0 when we talk about the turn-on characteristics of the power pole. Okay, do you mean VDS? VDS drop to 0? So for VDS dropping to 0, it is because at this point, ID is equal to I0, right? ID, the drain current, is equal to I0. So it means that at that point, so ID is equal to 0, I0. So it means that there is no latch current for diode anymore, right? So if there is no current, so this diode becomes reverse bias. Okay, so the current will flow like this. Okay, so so that VDS here will drop eventually to 0 within this period of time. Okay. Can ID becomes larger than ion? No, not for this case. It is because for this case, the magnitude of the current is limited by this. Okay, limited by this. The constant current source for this case. Okay, but in the applications here may not be a constant current source. Maybe the loading, maybe the load or open end. Okay, so it can high, it can target higher, but it, yeah. So just like Dr. Yang, mentioned. Okay, yeah, so it cannot happen. Okay, and actually, I think because of when you consider the characteristics of MOSFET, right? So I think for each application, you have the target current, okay, such that you apply a certain or corresponding level of the gate voltage. Okay, so anyhow, here not the case. Okay, okay. So here's the example, but just for your reference. Okay, for your reference. Now we don't need to do it. So uh, just for your reference, when you do practical things, it is because if you buy the components from the commercial market, there should be a data sheet. Okay, so in the data sheets there are many diagrams. Okay, for your information. So you just need to check. Okay, what is the temperature limit? What should be the, say, for example, this here. So what should be the maximum on-state gauge voltage? Yeah. So just for reference. Okay. So if you are interested, uh, take a look. Okay. So let's continue. So after turn on characteristics, we have the turn off characteristics. So actually, the phenomena or the trend are very similar to the previous one, but just the other way around. Okay, so very similar. So previously, we want to turn on the MOSFET, we need to do charging, right? But now we want to turn it off, so we just need to do discharging. So just simple like this. Okay, so okay, so now we want to turn it off. So initially, the MOSFET should be on, right? So it should be on. So according to what we just learned previously, so initially when the MOSFET is on, so it means that the ID here is equal to I naught, right? So ID here is equal to I naught at the very beginning, okay, correct? And then the gate source voltage is maximum, right? And the diode is reverse bias, and the VDS here is 0, right? This is because ID here is equal to I naught, okay? It's on, okay? And then now we want to turn it off. So we try to reduce the gate source voltage, okay? And then just similar to what we did, okay? So to some critical points, there's something happened, okay? So the first one is the VGS with I naught. It is because here we have the constant current source with the magnitude of I naught, okay? And then the other critical points should be the threshold value of the gate voltage, okay? And now we are doing the discharging. So the region here we call it turn off delay time. So previously we have turned on delay time, right? Very similar. Okay. So now discharging. Obviously, during this period of time, nothing changed. Okay, until reaching one of the critical points. Okay, so it means that the MOSFET remains on during this period of time. Okay, okay, and then down to this critical value, this critical value. So it means that the ID is still equal to I naught, right? ID is still equal to I naught. Okay? However, let's say at this very short period of time, VDS start to increase. Okay, VDS start to increase, and then when the gate source voltage down to this level, the threshold value, or actually below, right below this corresponding level of the gate source voltage, the drain current will drop. job. Okay, so you just need to remember the three operation regions of MOSFET. That's good enough, right? It is because say if we want ID is equal to I naught, so we just need to apply VGS with the blanket of I naught. Okay, if we want have some drain current, we just need to apply the gate source voltage beyond the threshold value. Okay, so you just need to remember those two critical points. Okay, so and then it's not that difficult to imagine how it works. Okay, so when the gate source voltage is below the threshold value, okay, so obviously completely off from the MOSFET, right? So ID should be equal to 0, and then it also blocks the input voltage. So VDS is equal to Vin. Okay, so turn on and turn off characteristics are very similar. Okay, but the trend or the change are just opposite. Okay, is it okay? Okay, all right. So this should be the last subtopic of topic 2. So we are going to learn how to determine the power losses of components or devices in switching power poles. Okay, so for in ideal case, so when the switch is on, so voltage should be equal to 0, right? So during the off state, the current should be equal to 0. So those are the ideal case. However, during the operation, there should be power losses. Okay, so the power losses can be come from many aspects, but here we just introduce you two aspects. Okay, so switching and forward or conducting. Okay, so here also for your reference, so this is the ideal case. Okay, but in practical, it look like this. Okay, yep. So it is because in power poles, the most or the major components should be the MOSFET and diode, and so most of the losses should come from them. Okay, and for the MOSFET, here we'll look at two categories. So conduction loss and switching losses. Okay, and then for the power diode, also the forward voltage drop. So this one is also the conducting power loss, and then is reverse recovery characteristics. Okay, so we will look at it one by one. So the first one is for the MOSFET. We call it conduction loss. So conduction loss. So from the word, so you should we should know that, right? So it should be loss during the operation of the MOSFET. Okay, so should be talking about its on state. Okay, so in on state, the MOSFET conducts drain current, right? Conducts drain current. But with the switching duty ratio, do you still remember duty ratio? A small letter D. Do you still remember? So its definition is the ratio of the on interval and switching interval. Okay. So if you don't remember, please do revision on topic 1. Okay, topic 1. Okay, then so here, yeah, actually this one comes from the basic definition of the Riemann square value. So here for reference, so actually our research waveform look like this, right? Just like a pulse string, right? So for pulse string, if we want to determine its root mean square value, so we have this equation, okay? And to simplify, just like this, okay? So A here is the amplitude. A here is the amplitude. and D here is for the time interval. Okay, so actually we can apply this to our case. Okay, so this one is the amplitude, right? This one A. Okay, and then here with the D is the duty ratio, right? D is the duty ratio. Okay, so we just need to apply here with D. Okay, so we just actually, so equation 2.2 comes from the basic definition of the Gould mean square value. Okay, it is because our resultant waveform also look like a not look like a actually is exactly the pulse string waveform. Okay, so we can adopt the previous the equation in the previous slide. Okay, okay, so with this equation we can calculate the current. Okay, and then we can use a very basic equation. Power is equal to I square R. Okay, so I, we have the square root D times I naught. Okay, so take square, so we have this. Okay, and then times the on-stage resistance. So that's how we can calculate the conduction loss of the MOSFET. Okay. Right, so this is the first power loss. And then the second power loss for MOSFET is the switching losses. Okay, so as mentioned before, right? So at very high switching frequencies, the power losses, the switching power losses should also be very high. Okay, but here I give you one more information. Okay, so at high switching frequencies, switching power losses can be even higher than the conduction loss. So we just learned the conduction loss calculation right in the previous slides. Okay, and then now we look at this. It is because this one is critical when the switching frequency is very high. Okay. Okay. So, do you find this waveform and this one familiar? Do you find them familiar? Actually, we saw them before. Do you remember? Here, this one is one of them, right? This is the turn-off characteristics. And this one, turn-on characteristics. Okay, so here describes the period of time that we turn on switching power pole, right? And this one is turned off. Okay, so it means that okay, so this picture combines the turn on and turn off characteristics of power poles. Okay, okay, so now we want to calculate the switching power losses, right? So P should be equal to V times I, right? So here we have the voltage and current. Okay, so we can times them together. So it is because all the things here are linear. So when we times them together, it's just like a triangle, right? Triangle. Okay, and the peak value should be equal to V in times I naught. It is because here is I naught, right? Okay, V in times I naught is the peak. Okay, and this is one of the switching power, and then the other one for turning on or turn off characteristics of power poles. So again, we have the same magnitude of the peak here, okay, but with different times of intervals. Okay. So with these two triangles, we can write down equation 2.4. Okay, equation 2.4. It is because if we want to calculate the power here, actually we can simply calculate the area of this triangle, right? So do you still remember how to calculate the area of triangle? Okay, the height times base by 2, right? So here we have 0.5 here, and then this one is the height times base, and we have 2 here, okay? So, but the other one is with different base, okay? So here we have, actually here is the summation of 2 triangular areas, right? Okay, and then to balance the unit, so here it is because now here we still need to calculate the power, right? Okay, and so at the end here we need to time or multiply with the switching frequency. Okay, so we can use this equation to calculate the switching losses of the power, MOSFET. Okay, so this equation comes from turn on and turn off characteristics of the switching power poles. Okay, clear? Okay, so after the MOSFET, we also have 2 losses for diodes. Okay, so the first one is the average forward loss. Average forward loss. Okay, so it means that this loss should be should happen. Okay, or we should have this kind of loss when the current pass through the diode, right? Okay, so we have this equation. So this one should become from P is equal to VI. Okay, but here we have this term 1 minus D. Okay, do you know why? 1 minus D. Actually, this equation corresponds to our topology, right? So we need to look when the diode is conducting here, right? When diode is conducting. So if we want it conduct, so it means at that moment or at that period of time, the MOSFET should be off, right? So when it is off, it is open, and then here the constant current source or the current I0 freewheels through the diode, right? Okay, so that should be the period of time when MOSFET is off, right? So that's why the period of time for diode on should be 1 minus D. Okay, can you get it? Okay, can you get it? Okay, once again, the diode is on when the MOSFET is off. Okay, so if D is the duty ratio of the switching power pole, so here we should have the term 1 minus D. Okay, 1 minus D. Okay, this is because the diode can only conduct during this period of time. Okay, so that's why we have the equation 2.7. Is that okay? Okay. Okay, so the last power losses in power poles, and that's for the diode. Okay, so here should be the ideal case, right? So the forward current from anode to cathode should goes to 0 when the if the diode goes from forward bias to reverse bias, right? So actually, diode is also under switching, right? So from forward bias to reverse bias or vice versa. Okay, so this kind of switching actually also cause or induce losses in diodes. Okay, so that's the ideal case. So when there is a switching for diode, there should have no voltage drop, okay, or power losses. However, in practical, um, yeah, actually we can see this for reference. Okay, so actually I mentioned, so the semiconductor materials can be classified into two types: N-dope and P-dope, and or N-type or P-type. So in P-type here, the majority carriers will be holes, right? And here the majority carriers will be electrons. Okay, so when the diode is under switching, say for example from transitions from forward bias to reverse bias, so some minority carriers cannot back to its or back to their initial position. Okay, it still takes some time for them to return to their position. So that period of time can induce losses. Okay, so that is the statement here. Okay, so the free minority carriers need some time, okay, to go back to their original position. Okay, and this period of time we call it reverse recovery time. Okay, okay, so that recovery will induce or will make this kind of waveform. Okay, it is because the minority carriers need some time to go back to its original position. Okay, so but here luckily, so we can see that it is approximately equal to a triangle, right? So we can use a relatively simple calculation to estimate its area. Okay, so again, height times base, TRR, and then divided by 2 is the triangular area. So here, it's here. And this one is equal to Q, actually, is the charge. Okay, is the charge. Okay, and if we want to calculate the power, okay, so we need to times V and switching frequency. Okay. Okay, so that's how we can determine. That's how we can determine the switching losses of diodes in switching power poles. Okay. All right. Yeah. So in this topic, we just learned 4 types of power losses in power poles: 2 from diodes, 2 from transistors. Okay. Yeah, and this in-class exercise actually is not that complicated, but will help you to understand or have some practice to get using the previous equations to calculate the power losses. Okay, yeah, and so here is the converter. Okay, and then here give you at the turn on and turn off characteristics, and some very important parameters are given. So for example, I naught is given, I naught here is given, and then the switching period is given here, input voltage and output voltage, and yeah, so this one is also given, right? So on-state resistance is given. So this one helps you to calculate the conduction loss of the MOSFET. Okay, and then the question asks you to calculate the average switching power loss PSW and average conduction loss conduct in the MOSFET. So this one here, or the time information, can help you to calculate the switching power loss. Okay, And then the resistance can help you to calculate the conduction loss. Okay, and then the part B asks you to calculate the average forward power loss in the dial. Okay, with this information. So do you still remember P is equal to VI? But for dial, it's kind of tricky. So we have a term for duty ratio, okay, in the equation. And then part C asks you to calculate the efficiency of the converter, taking into account the losses calculated in both parts A and B, okay. So this example looks very simple, but actually you need to use the period knowledge that we learned in topic 1 or and topic 2. Okay, so please try to think about that, and then yeah, to try to solve the problem. Okay, and I may give you 10 to 15 minutes depending on your progress. If you can finish early the problem, please take a rest. Okay. Of course, feel free to ask any questions during the in-class exercise and break.